Hello, everyone. My name is Christine. I'm an early college student in the engineering program at Rockville. Behind me, I have Quinten. He is also an early college student in the mathematics program. On this side, I have Faasil. He's an early college student in the mathematics program as well. All three of us are at Rockville. So, as you guys can probably see on your screens right now, we are talking about Julia sets. And just to give a little bit of an intro to what a Julia set is, you see this graphic on your screen is not just something we pulled off of Microsoft. It is actually a Julia set. So Julia sets at its basis form is a fractal, and these fractals are basically complex iterations that are visually represented into these beautiful images. The colors, they actually have a significant meaning as well, and just to keep that in mind as we progress through the presentation. So this is exactly what we'll be talking about today. We have complex arithmetic, the boundary mapping principle, the quadratic family of the Julia sets that we'll be focusing on, C equals 0, and a bit of the chaotic stuff that we have been talking about in our class, Julia sets, a specific type Cantor sets, how to form a Julia set by hand, self-similarity, how to compute an algorithm, and some Julia set animations that we have computed for you guys today.
So to begin about Julia sets, we have to know where they reside, and they reside in the complex plane. The complex plane houses complex numbers, surprisingly enough. And complex numbers are a combination of both real and imaginary numbers. So things like 1 plus I are graphed here. There's two axes, one on the vertical, which is the imaginary, which houses things like I and negative 3i, and the horizontal, which houses the real numbers like 1, 2, and 3. 1 plus I is up here where 1 would be, and so on. And then up here we have the polar representation, which will be important for proving a few things later. And in essence, it can be written, a thing by x plus iy can be written as re I theta. Now, in order to really continue our topic, we need to talk about addition, multiplication, and square rooting, and that will be on our next slide. Complex arithmetic. So, addition. It's simply the way we do vector addition. We do head to tail, and we have w and z as their points, and we go to z plus w. Quite simple like that. Then we have complex multiplication, which is a bit more fancy. So we have the 2 points w and z with respective angles theta and phi. In order to multiply them together, we multiply the magnitudes of w and z to get cw, as that's the magnitude, which is the length. And the angle is simply theta plus phi, which is over here. So when we square it,
systems have 3 main properties. It has a dense set of periodic points, transitivity, and center dependence on initial conditions. So let's start with...
When we square it, we simply square the magnitude and double the angle. And that would allow us to go from the square to this shape. I'm not sure what to call this one. So when you square all of these, we get this. And on square rooting is simply the opposite of that. We square root the magnitude and have the angle, and like with all numbers, it has 2 square roots, the positive and the negative. The important part about this is this little thing. This fact that in the complex plane, a circle, or as we're going to see, the quadratic, the Julia set, when c is equal to 0, which is a unit circle, when a unit circle that has the origin is square rooted, we get this figure 8. This is going to be very important in building the Julia set later on. And this is also quite important, the boundary mapping principle. In order to prove, in essence, it says that this point over here is z0, and this region, which I'm just going to call A for now, is inside. When we apply a function q of c to each of them, and z0 is still inside this area when we apply this. And that applies over here as well when we square it. So anything that was in this little smiley face over here, when we square the region and square the point, it's still inside. So the shaded region stays shaded, and so on like that. And now to introduce what we're going to be making the Julia set out of, the quadratic family.
Okay, so like you guys see on the screen right now, we have q of c of x equals x squared plus c. As many of you guys know, this is a parabola, and we've seen this multiple times in our classes, so this is what we're focusing on today. So
we
if I
set
go
k
on
to be
to
between 0 and to be less
So,
than
sorry, for the first graph, we see that we have an x squared centered at c equals 0, and we see a y equals x line pass through, where the x squared and the y equals x, where they intersect is what we call fixed points. So the fixed points are really important because, as you can see, there are some green lines coming out of that, and to say simply, the green lines are iterations. So what we like to do is we take the output and we make it as our new input. For example, if we have, let's say, x plus 1, and we say we want to start out with 0, we do 0 plus 1 equals 1. We take that 1, we move it into our x, now we have 1 plus 1 equals 2. We continue this and continue this on to infinity. So right here, we see these iterations, these green lines, and as you can see, they're coming out of that fixed point, and these are, we like to call this behavior repelling. So it's coming out of the fixed point and it's tending towards infinity.
and then with enough n,
We have a c equals a -1 for our attracting point, and we start out with a number, any number we'd like. We see that behavior come towards the fixed point. As you can see, it's kind of going in like a square. We like to call this an attracting 2 cycle.
each other will be on opposite ends of the on the opposite
And last, we see for c equals -3, you can see it slowly having a bit of chaos, as we like to call it, around the center. And you can see it's kind of that one line that's coming out and going towards infinity. So this is a repelling point, but we really want to focus on how it's slowly moving out to infinity. And this is where Julia's sets really come into relationship to all of this. So as you can see, you have about 3 different lines right now. You have that green line from the c equals -3. You have a red line and a blue line. So the green line is doing the same thing. It's slowly iterating until it finally goes out to infinity. You see that red line only has 2 or 3 iterations before it's moved out to infinity completely. And you see that blue line is kind of doing what that c equals -1 was doing and just going in a 2 cycle, not really moving anywhere. Julia's sets will show the behavior moving slowly, quickly towards infinity, and it will show these iterations in these visual representations that you guys will see in the upcoming slides. And I do want to point out right now that, as you can see, most of these numbers that I have attached for C are real numbers. We will mostly be focusing on complex numbers. This is just a great way to show some of that behavior in an easier way to digest.
It's incredible that we can take all of these types and categorize them into one.
Now on our next slide, we will prove the chaotic nature of the Julia set because we took a chaos theory class, so thus we are going to be explaining why it's chaotic. Devaney says that chaotic systems have 3 main properties. It has a dense set of periodic points, transitivity, and sensitive dependence on initial conditions. So let's just start with a dense set of periodic points. Dense set of periodic points simply means that there are periodic points in any interval that we choose. In this case, we're going to be using the polar representations to make the calculations a bit easier. Transitivity simply means that a transitive dynamical system has the property that given any 2 points, we can find an orbit that comes arbitrarily close to both. So pick a point and pick 2 points. We find an orbit that comes as close as we want to either of them. And then sensitive dependence on initial conditions is probably the first thing that most people think of when they hear the word chaos. Or, in layman's terms, the butterfly effect. Small effect in the start, big effect at the end. So, we first start with trying to prove the first, a dense set of periodic points. That means that for any 2 theta, theta 1 and theta 2, there is going to be a theta of that's going to be part of our graph. So, and since it's periodic, we know that after a certain number of iterations, or n iterations of q naught, which is going to be our function that we're going to be iterating on, it's going to be the e to the I theta, which is the polar representation, if you guys remember that, is going to be equal, once again, to e to the I theta. But the same thing also applies that when you iterate e to the I theta, we're going to get this. We're going to get e to the I times 2 to the n theta. So, what do? We set them equal to each other, do a bit of rearrangement, and we get 2 to the n theta plus theta plus 2k pi. 2k pi, as some of you may remember from your trigonometry days, is simply just the fact that circles go round. A bit more rearrangement later, and we get theta is equal to 2k pi over 2n minus 1. This is going to be what we want to prove. So we set k to be between 0 and to be less than 2n minus 1, and we finally get this. that this, since this is our theta, we want this to be between these two, so we simply subtract them, and we get 2 pi over 2n minus 1. We set n, or the number of iterations, to whatever number we want in order to land between these, thus proving that. And these show the different k values and the different points on the graph. So that would prove the density of the existence of dense periodic points. Transitivity and sensitive dependence follow in the same suit, since we can use the same equation again. Transitivity follows since that, and every time we iterate, the arc between these, every time we increase n, the arc between these things expand by a factor of 2 due to the fact that when we square it, we square also the length. If you guys remember that for the magnitude. And then so with enough n, we are able to go around the entire circle and thus have any point anywhere we want. And sensitive dependence on initial conditions also has the same property, since that after a certain amount of n, 2 points that started close to each other will be on opposite ends of the opposite ends of the circle, and that would prove the chaotic nature of the set. And now to explain Cantor sets.
So Cantor sets. Cantor sets are another way of to do iterations. So right there on our screen, we have a closed sequence of 1. So a Cantor set is a closed set. Points are systematically removed indefinitely until what is looked like dust. We have that closed set of 1. We take out a third, and we get 1/3. We take out another third, we get a ninth. We repeat the process till we have, as you can see at the very, very bottom, 181. And you would just continue this process to infinity until what basically looks like left is dust. So Julia sets have 2 forms: Cantor sets, totally disconnected, non-touching point, or connected sets. So the totally disconnected would be kind of what you guys see at the bottom, and the connected sets would be that full sequence of 1 at the very top. And when the orbit of 0 tends to infinity under iterations of QC of z equals z squared plus c, then Q of c has a Cantor set type Julia set. Now this is a really interesting point to point out, because we can take any Julia set, we put in all these numbers, and we can automatically say at any point, this is a Cantor set type Julia set because that orbit tends to 0. And it's incredible that we can take all of these types and categorize them into one specific thing. And we want to say, though, that just to be clear, that the most basic Julia set to form is where the absolute value of c is greater than 2.
And so these patterns become quite complex very quickly.
Thank you.
And then here we have one.
Okay, so now we're going to form an actual Julia set. So what's important about to tell whether points leave whether points go to infinity or not, which is really what the Julia set is, it shows the chaotic points, is that when points have a modulus that's greater than c, meaning that the distance from the origin is greater than c, then we know for sure that they go to infinity. And that's because when we keep doubling the modulus of subtracting, then it's going to go greater and greater to infinity. And so we want to find the points that are going to leave the circle. And to do that, we can take pre-images of the function Q of c. And so what we looked at earlier with the complex arithmetic is that the pre-image of a circle gives us this figure 8 shape. And so we're going to start with this circle, and we know that all the points that are outside of the circle definitely go to infinity. So they're not that interesting to us. But we don't know what happens to the points inside the circle. So what we're going to do is we're going to take the pre-image of that circle by subtracting and taking the square root to find this new figure 8. So the points outside of that figure 8 definitely go to infinity after they leave the circle. But the points inside the figure 8, we're not really sure. So we're going to take another pre-image. And then we find these smaller figure 8s. And so these points inside the figure 8 are going to take longer to leave the circle eventually, but we still don't know what happens inside the purple. And so what we can do is keep repeating this infinite times until we get these really, really tiny figure 8s, where only the perfectly black points are the ones that never leave the circle. And so those points are too small for us to see, but there's no intervals left. We've removed so many points that there's only singular points left. And so what we can see is that even if we zoom in on this small section, that these figure 8s keep continuing to infinity. And so this is showing the Cantor behavior that we were saying earlier, how we keep removing area until it's like dust left. And so those black points are the real Julia set. And the rest is just showing the behavior that goes to infinity.
So, as many of you guys probably see in that last slide, there was a pattern going on right there. And we like to call this interesting phenomenon when c is not equal to 0, self-similarity. It usually appears around the boundaries of a filled Julia set. So right, as you guys can probably see on the screen, at the very top, we see a Julia set. It kind of looks like it's already repeating by itself, a little pattern there. We take that square and we zoom in, and we go to the bottom left, and we see that's the zoomed in square. And we go even closer, take that square, and move to the right, and we see that's another set. You can see that they just keep on continuing and continuing on to infinity. All those little tiny black dots are the exact things that are in that square. So when Julia sets are Cantor sets, the filled Julia sets are self-repeating points, and that is why we get these decorations that repeat until infinity.
We actually measured the time that it took to leave that circle of radius c.
Okay, so now we're going to actually generate our own Julia sets using a computing algorithm. And so there are two possible methods to do this, but we've just used the first because it looks better in our opinion. But for every pixel in basically a big image, an image is just a big array of pixels, we're going to equate it to some point, and then we're going to iterate it a certain number of times and see if it eventually leaves that circle of C that we were talking about earlier, the points that we know definitely go to infinity. And we're just going to color all the points on that image based on how long it takes for them to leave that circle. And then there is also a second method, which we haven't used, which is to choose any point and just calculate the backwards iteration. Because we know that any point that does lead to infinity had at some point a lot of chaotic behavior, but we don't know what it was, so we can just go back many, many points, and then it's going to eventually visit every point, and that's because of chaos. So here's an animation that we've rendered of different Julia sets, and on the left we see just a freeze frame of one of them. And so what it's doing is it's scrolling through all the Julia sets from C equals 0 to C equals 2. And what it shows is that as soon as it goes from that transition from the 0 becoming black to colored, we know that it becomes a Cantor type Julia set and it breaks up into these infinitely small points. But before that, it's just a big circle of Julia set. And we can look at more examples of these Julia sets when we change what the C value is, and they look quite different. They're really hard to recognize. Here, these are both Cantor type Julia sets, so there's no intervals, it's just individual points. And what we can see is that points that are even very close to each other, for example, on the right image, there's some purple points that are quite close to orange points. So they're very, very close. However, they have very different behavior. The purple ones take a long time to go to infinity, but the orange ones don't. They go to infinity very quickly. And so these patterns become quite complex very quickly. And then here we have one more. Here we can really see the self-similarity in the Julia sets. So this left image is just a zoom in of the right image at the bottom left. And so these big spirals that we can see from far away are really just made up of many, many tinier spirals, which those are made up of even tinier spirals. And so that is really what makes Julia sets cool. Here we have a few references.
Okay. Thank you guys for listening.